Let's start with an introduction to logarithms before we actually define them mathematically. Parts A through F below are similar to a puzzle that is more than 2,100 years old. Mathematicians first created the puzzle in ancient India in 2nd century BC. More recently, about 700 years ago, Muslim mathematicians created the first tables, allowing them to find answers to this type of puzzle quickly. Tables similar to them appeared in school math books until recently, due to the invention of slide rules and calculators. Here are some clues to help you figure out how the puzzle works. So what I'm going to ask you to do is to actually go through, look at these clues, and then use them to find the missing pieces of the puzzle below before moving on to the next slide to see the solutions. This will seriously help in your understanding of logarithmic functions and should take you about 5 to 10 minutes to find the pattern. So again, it's really important that you take this time to do this so that you actually get a good understanding of how logarithms work and what they are. So go ahead and pause the video now, work this out on your worksheet or in your math notebook, and then when you feel like you have a good grasp of the answers, go ahead and click next and you'll see the next slide with the solutions. In the last slide, hopefully you were able to see this pattern. 2 to the third power is 8. 9 to the 1/2 power is 3. Remember, anything to the 1/2 power is the same thing as the square root of that. 5 to the 2nd power is 25. 10 to the 4th power is 10,000. So a logarithm is essentially just a power. So 2 to what power is 16? And that's 4. 5 to the 3rd power is 125. 2 to what power is 32? And that's 5. So what to the 4th power is 81? That's 3. When you take 3 and put it to the 4th power, you get 81. What number to the 2nd power is 100? And that's 10. And then 100 to what power is 10? So we can look at that. 100 to what power, and I'll just let that be x, is 10. Okay, so to get from 100 to 10, you're having to square root it. So that's going to be 100 to the 1/2 power. Now let's mathematically define logarithms. How would you solve equations like x plus 5 equals 8, 3x equals 10, 2 to the x equals 8, 2 to the x equals 10? So for example, to solve this first one, you would, right now we're adding 5 to x, so you would do the opposite of adding 5, which is subtracting 5. Here we're multiplying x by 3 so that to isolate the x you would divide by 3. We learned in the last section we can solve this 2 to the x equals 2 cubed because 8 is the same thing as 2 cubed, so we'd get x equals 3. We come into an issue here though where we have 2 to the x equals 10. 10 isn't 2 to any specific integer power. We don't know what that is. So right now we don't have tools to be able to solve this, and this is where logarithms come into play. In order to solve an equation like 2 to the x equals 10, we will need the inverse function to the exponential function to get the x out of the exponent. This is where the logarithmic function comes in. As shown in the introductory puzzle, a logarithm is just a power. Mathematically, to define this, the logarithm function to the base a, where a is greater than 0 and cannot equal 1, is denoted by log base a of x, and is defined by y equals log base a of x if and only if a to the y power equals x. So a to the y equals x. We read y equals log base a of x as the logarithm with base a of x, or the log base a of x. Some other things to note. So the common logarithm, if you ever see log of x, So notice there's no base written here. That actually means log base 10 of x. It occurs so often that we don't end up writing base 10. So if you ever see just a logarithm without a base written there, just know that that means that it's a base 10. Just like we see things like x, that means 1x. We just don't write that 1 because that occurs so many times or so often. And again, this is x to the first power, but again, we don't write that first power. But we know that it's there, it's implied. The other type of logarithm is called the natural logarithm. So if you see the ln of x, so this is an L, not an I, this means log base e of x. And remember, we learned about base e in the exponential function chapter or section. And this is derived from Latin for Logarithmus naturalis. That's why we call it ln for the natural logarithm instead of nl, because again, it's derived from Latin where the logarithm word is written first. So again, if you ever see ln of x, that means log base e of x. So let's practice converting from logarithmic to exponential form. Remember in the last definition, y equals log base a of x if and only if x equals a to the y. So for example 1, let's just practice on changing the exponential statement to an equivalent statement using logarithms. Okay, so this would be log base 1/4. So the base of the exponent is the same thing for the base of the logarithm of 6 equals x. So 1/4 of 6 equals x. This would be log base 10, which is just log of 7 equals m, because again, the log always equals a power. Letter C would be log base e, which is the natural log, of 5 equals 2t. Now let's do the opposite. Let's change from the logarithmic statement to an equivalent statement using exponentials. Okay, so the base here is 3, so 3 to the x equals 5. When it's not written, the base isn't written, remember that's an implied base 10. So I'm going to just rewrite that so you can see that. So 10 to the x equals 5. Again, when it's not written there, and now this is the natural log, this is an implied log base e. Now, ln of x is the same thing as log base e. So e to the 5th equals x. For another video over finding equations of exponential functions, go here.